In a general way, as an introduction, we can say that continuous functions are those whose graphs can be traced without lifting your pencil. The graph shown can be considered a continuous function because the function is defined at all places and it has no breaks or jumps. A function is considered to be discontinuous when there are breaks or jumps within the function. In the graph shown, we can see that there is a jump in the function at x equals 3. Thus, the function is discontinuous. That was the simple and the visual way of determining if a graph is continuous or discontinuous. However, the visual method has several disadvantages since it cannot measure really big numbers and it cannot measure cases in which a graph is continuous at some places and discontinuous at others. Now we're going to learn about the mathematical process that must be undertaken to determine the continuity of a function. The definition of continuity in calculus relies heavily on the concept of limits and it is divided in three main steps. For a function to be considered continuous, it has to pass these three tests. If one of the tests fails, the function is considered to be discontinuous and the process must be stopped. The function is defined at x equals a. That is, function of a equals a real number. This means that the function must be defined at the given point of x. The limit of the function as x approaches a exists. This means that the limit must exist and it must be the same from both the positive and the negative approach. The limit of the function as x approaches a is equal to the function value at x equals a. This final test means that the value of the function defined at a certain variable must be equal to the value of the limit of the function. Let's start by doing some problems. In this first problem, we cannot factorize. We're trying to find the first step, which is finding the value of f of x. In this case, it's f of 2, so we have to replace the 2 in all the x's inside the function. After replacing the values of x, we realize that we end up with a value that equals 0 over 0. This value is undefined. We can conclude that f of x is not defined when x equals 2. So we end the procedure there and we don't have to do the other tests because we know that the function is not continuous. Here we have a more complex example. This will include the piecewise functions. We'll start with the first test. In the piecewise functions, we have to remember that the first test is used with the function that has the greater or less than equal sign. Then we just have to replace the values as we did in the previous example. we get 1 as a result, which means that the function is defined at x equals minus 1. Now comes the second step. In this second step, we have to get the limit of the function. However, since the first piece of the function does not have any x's, we can determine that the limit equals the number. After substituting, we realize that the limit from the positive approach equals 1, the same as the one in the negative approach. So we can say that the limit of the function equals 1. In the third and final step, we just have to compare the value of f of x when x equals minus 1 and the limit when x approaches minus 1. If these both are the same, we can say that the function is continuous. If they're not, the function is discontinuous. However, in this example, we have that both numbers and both values are equal to 1, so we can say that the function is continuous.
Like the legend of the phoenix,